let's look at one more level curve example. Let's look at this function. F of xy from 6 over, thank you, x squared plus y squared plus 2. And let's talk about all the things. Let's talk about domain, range, level curves, etc. So, domain. No square roots. Great, don't get rid of that. No logarithms. Great, don't get rid of that. But I do have a fraction, which means I do have the possibility of dividing by 0. So I need to make sure that I exclude any values of x and y that make the denominator equal to 0. Fortunately, there aren't any, right? If we try solving that, we're not going to get any real answers because we know, well, in fact, if we bring the minus 2 over, x squared plus y squared equal to -2, that has no real solution. So our domain is everything. Now I want to point out, our domain doesn't consist of numbers. Our domain consists of coordinates, x, y pair. Come on in, thank you. So the domain here, if you wanted to be very short about your answer, you would say the domain is R2. Some people say R squared, but R2 is the more common way of saying it. The more lengthy way of writing your answer is the set containing all points x comma y such that x and y are real numbers. So that's our domain. No domain issues. We get the whole entire real plane R2. Range. How am I going to think about the range here? Well, I know that. So again, the range, it can be kind of difficult to have a method that works the same every time. Right? There's no real kind of algorithm for finding the range. Sometimes it's not really possible at all. This one it is. We can kind of think about where is this thing large and where is this thing small. So I want to see how small can 6 over x squared plus y squared plus 2 be. Well, to make a fraction small, we make the denominator big, right? The bigger the denominator is, the smaller the fraction is. How big can that denominator be? Really big, like infinitely big. So if the denominator can be infinitely large, the fraction can get as close to 0 as possible without actually ever being 0. So we can get almost gets to 0. How large? Well, same sort of idea. If I want to make my fraction large, I want to make my denominator small. So what's the smallest the denominator can be? A real nice integer number. How small can that be? 2, right? Because I assume you're making the choice that x is 0 and y is 0. Right? That's the smallest those can be when they're getting squared. So 0 squared plus 0 squared plus 2 is the smallest the denominator can be, which means the biggest it can be, which is 3. Now, another way, maybe a slightly more formal way to tackle this particular problem. Here's an idea. If you see an x squared plus y squared, think about it on its own. And you're going to see a number of functions where you do have an x squared plus y squared, or a negative x squared minus y squared, which is just negative x squared plus y squared. So if you see an x squared plus y squared, you know something about that. You know that no matter what x and y are, this is always bigger than or equal to what? And it can be as big as But there's no upper bound for that, I should say. Okay, I'm going to add 2 to everything because what I'm going to try is I'm going to try and make this look like that. So if I add 2, 0 plus 2 is less than or equal to x squared plus y squared plus 2 is less than infinity plus 2, still infinity. And then I'm going to take the reciprocal of everything. Now, here's an important thing to know. When you take the reciprocal of both sides of an inequality, it changes the direction of the inequality. What's bigger, 2 or 3? I mean, it's not a hard question. It's 3. Okay. Okay, slightly harder question. What's bigger, 1/2 or 1/3? 1/2. So when you take the reciprocal of both sides of an inequality, you change the direction of the inequality. So here, if I take the reciprocal of all 3 sides, I'm going to get 1. I feel like there's something my brain is missing here. Oh, I forgot the 6. That's okay. Fine. So I'm going to get 1/2 bigger than or equal to 1 over x squared plus y squared plus 2, strictly bigger than 1 over infinity, which is essentially getting closer and closer to 0. And then to finish off the problem, we can multiply, finish off the range finding, we can multiply everything by 6. 6 times 1/2 is 3. 6 times this is 6 over x squared plus y squared plus 2. And 6 times 0 is 0. So if you have an x squared plus y squared showing up, you can try to do something like this, where you start with this sort of thing and manipulate your expression until it looks like the function you're actually dealing with. It worked most of the time. So our range is exclusive of 0 up to 3 inclusive. Cool. Also, knowing the range means we now know what sort of level curve values we're allowed to have. And because literally the level curves are setting the function equal to a number and then seeing what the graph in the xy plane would look like. Well, we are only allowed to set the function equal to numbers that are in its range. If we can't set this function equal to 4, you won't get anything. So let's talk about the level curves. So again, we have this function. And so we're going to do a few level curves, but I'm going to again talk about kind of the quote unquote best way to do it. And where did my stuff go here? Sure, so let's find level curves for C equal to 1/4, 1/2, 1, 2, and 3. Kind of a lot. I don't want to solve 5 equations. Neither do you. So instead what we're going to do is we're just going to set the function equal to C. And then we're going to try to see, no pun intended there, we're going to try and see what this curve should look like. And again, I'm focusing in on the x squared plus y squared because that is a common theme you will see, not in every function of 2 variables, but in a lot of them. Welcome, thanks. So I'm going to try and isolate the x squared plus y squared, which means I'm going to take the reciprocal of both sides first. So I'm going to say x squared plus y squared plus 2 over 6 equals 1 over c. And then I'm really going to try and get the x squared plus y squared by itself. So multiply both sides by 6. Subtract 2. Great. I know what my level curves look like now. What kind of shapes are my level curves? That's a good question. Let's plug in one value. So let's say let's do c equals 1. We did c equals 1. We'd get x squared plus y squared equals 6 over 1 minus 2. We'd have x squared plus y squared equal to 4. And what kind of shape is that? Everybody? It's a circle of radius what? 2, centered at the origin. But more generally, all of my level curves are circles centered at the origin. And the radius depends on C. The radius is just the square root of 6 over C minus 2. I'm trying to do not all the work in the world, right? I would rather just do this so that then I can talk about each of my level curves. So for C equal to 1, we're going to get a circle with radius square root of 6 over 1 minus 2, which we already figured out was 2. For C equal to 2, the radius is going to be the square root of 6 over 2 minus 2, which is the square root of 1. For C equal to 3, the radius is going to be kind of dumb. It's going to be 6 over 3 minus 2, which is 0. A circle of radius 0 is just the point at the center. So that's just a point. If my C value is 1/2, my radius is going to be 6 divided by 1/2 minus 2, which is 12 minus 2, which is the square root of 10, which I know is bigger than 3 and less than 4. And finally, for C equal to 1/4, the radius is the square root of 6 over 1/4 minus 2. 6 times 4 is 24, minus 2 is 22. So it's the square root of 22, which is between 4 and 5, right? When I'm thinking about these radii, I'm just kind of trying to get a vague idea of what integer numbers they're between. Yeah, so then we should graph the level curves. So, and sometimes I use different colors to kind of distinguish between them and try and be somewhat good about my picture here. Welcome, let me see that, sir. All right. Thanks. So, you know, it can be challenging drawing circles. So let's see. So I'm going to start with the smallest one. So there's my level curve for C equal to 0. And here's my level curve for C equal to 1. So sorry, to 2, apologies. And I feel like I'm so sorry, I made a mistake there. That's not C equal to 0, right? The radius is 0 when C equals 3. I'll zoom in for a minute. Stream close up. Wow. All right. I'm going to say a thing that's going to make me feel old. You guys get that reference? Extreme close up? It's fine. It's okay. It's from Wayne's World, which I know is a movie of my era, not your era, but it just seems like such a natural thing to say, extreme close up. But it's okay. I've dated myself. It's all right. I'm an older man. Wayne's World is a good movie. It's worth watching. It's entertaining, but it's probably, I don't know. I say that not having watched it many years, it might not hold up at all. Maybe it's terrible. So if it's terrible, don't tell me. I'm not going to watch it. All right. Anyway, so C equals 2 is the circle of radius 1, or the level curve of radius 1. And C equals 1 is the level curve for the circle of radius 2. Whoops. Okay, come on. Try to draw the best circles you can. So we can see here that as we go lower, our circles get wider, right? Because the C value is, again, it's the height that your function is at. So the higher we are, the smaller the circles are. The lower we go, the wider the circles get. So we can draw another one. If C equals 1/2, we get the square root of 10, which is not quite, or it's actually a little bit bigger than 3. I'm not trying to be, good thing. I said, I'm not trying to be perfect here, and I'm living up to my not perfectness. Well, that's an okay circle, I guess. And then finally, so I actually keep it writing down the radius instead of the level curve value. That's not good. It's not C equal to root 10, it's C equal to 1/2. And then finally, for C equal to 1/4, the square root of 22 is somewhere between 4 and 5. Whoops, come on. So yeah, that last circle is a little bit not great. So the idea is you can take these circles and stack them up. Right? C equals 1/4 is the lowest one, and then higher and higher and higher and higher. And it would look, now we're not being asked to draw the 3D curve, right? You're really only being asked to draw the level curve. But the idea here is up here at 3, we've got this, actually we've got this nothing. All right, the radius is 0. C equals 3. And then as we move outwards, or as we move down, like to C equals 2, you get a circle of radius 1. As you move down to say C equals 1, you get a circle of radius 2. And it kind of does this thing like this. You get a really big circle. So, oh, sorry, you can't see all that. It kind of looks like, this is not going to be the best description, but I think it's an all right description. If you have like a circular blanket and you start like picking it up from the middle, it would kind of look like this. Right? It's pointy at the top and the circles get wider as you go out. There's probably other good ways of describing this as well. But what I want to mention here is it just doesn't go straight down. Right? It's not like a cone because we're not, for every one you go down, you're not having a radius that's one bigger. It does start out that way, right? At the top, at 3, your radius is 0. You go 1 down, your radius increases by 1. You go 1 down again, your radius increases by 1. But then after that, it starts to kind of flatten out. And really, you could keep choosing smaller and smaller values of your height and getting really, really big radii. So for example, you could pick something like C equal to 1/1000th, which is still above 0, and your radius would be some square root of 6 over 1/1000 minus 2, which is a big number. It's the square root of 5,998, which I don't know what that is, but I know it's large. So as you get lower and lower and lower, you get circles that are wider and wider and wider and wider and wider. And this thing just kind of blankets out forever and ever and ever. Kind of neat. So level curves, right? We're supposed to imagine this as the ones with the higher values are literally higher up, the ones with the lower values are lower down. Oh, can I move up? Hopefully, yeah. I'm going to zoom back out. There we go. Okay. Also, just as a reminder, for the people on Zoom, no one can see the chat now. So if you want to chat and not have everyone see it, that's fine. You can send me a private message and ask me a question, and no one in the chat will see it either. So your messages are private now if you're on Zoom. Also, if any of you want to ask me a question and don't want the whole class to hear, totally get it. You can get on Zoom. Just make it quiet because otherwise we'll probably have a feedback issue. But you can totally get on Zoom and ask me a question that way. You're also always just welcome to ask me questions. But I know not everyone is comfortable saying things they might like. Yesterday, not this class, someone at the end of my 17A class was like, "Oh, James, can we talk about this? Okay, can we talk about this question?" I'm like, "Yes, we can totally talk about it." And this would have been a great question to have asked during class because I'm sure everybody wanted to see this and I kind of wanted to talk about it. I just ran out of time. So if you have a question you think you would like to hear more about, you really should ask because probably most, and especially all of you being in the same class, you probably all have the same sorts of questions. So don't be shy. Fortunately, I can talk for a long time. So if you don't have questions, I can say things. And the next thing I wanted to say was we're going to talk about limits. More limits. Where'd you go? Limits. There we are. All right. So when it comes to limits in this class, one of two things is going to happen. Most of the time, probably, the limit's not going to exist. And the way you're going to show the limit doesn't exist, this would be a perfect time for a Mean Girls clip. The limit doesn't exist, right? Okay. Anyway, most of the time you're going to show the limit doesn't exist by showing that the limit along two different paths is a different value. But sometimes you're going to pick a path and another path and another path, and you're going to keep hitting the same value. That doesn't mean the limit exists necessarily, but it means it might exist, and we might have to start thinking about trying to show it actually exists as opposed to showing it doesn't exist. And most of the time, showing the limit exists is a lot more challenging than showing it doesn't exist. We'll get there. There's typically two different things that happen there as well. So let's talk about some examples where, well, let's actually just talk about some examples. I'm not going to give away the ending. I would totally give away the ending. To books, to movies. One of my wife's least favorite qualities about me. We were reading these books together. I was like, oh, did you get to the part where this happens? She's like, no. And that's like the end of the book. Thanks. I was like, oh, sorry. I thought you'd gotten there already. So if we plug in 0, 0, what do we get? Nothing good. 0 over 0, which I want to, again, I'm going to emphasize it probably every time. We don't know what that is. It's not necessarily 0. It could be 0. It could also be 17. We don't know. It could also probably not exist, which is going to be what actually happens.
In 17b, wouldn't we use L'Hopital's rule or something like that?
Yes, but that's an excellent point. L'Hopital's rule doesn't work for multivariable functions, which is too bad. And because the problem here is like, when you want to take the derivative with respect to x or y. The problem and the issue really is you're not limited in the directions you can approach 0, 0 from. In 17a, you could only approach x from the right or the left. So you're kind of approaching, pardon. You can only approach the point 0 from the right or the left, which means you're always thinking about how the function is changing as x is changing. So taking the derivative with respect to x is sensible because you're only thinking about how x is changing. But when you start introducing functions of x and y, you have a lot of options as to how you can come at that point. Right? You can be super sneaky. There's lots of ways to get there. So we can't just think about how the function is changing as x is changing. We also have to think about how the function is changing as y is changing. And that really eliminates the possibility of using L'Hopital's rule. So instead, we do this thing where we come at it from different paths. And, oh, question, sorry. Sorry, could you say that just a little bit louder? Definitely. More generally, you can use any path that goes through the point you're approaching, which is why most of the examples we do with limits are going through the point 0, 0, because there are lots of paths that go through the point 0, 0. So I will just remind you, here is a list of very common paths. Y equals x. Y equals x to some power, which I suppose is also y equals x, but they feel a little different. X equals y to some power. Y equals a multiple of x. X equals a multiple of y. And then my favorite ones that get forgotten and usually give us some of the best information possible, y equal to 0 or x equal to 0. This list is by no means exhaustive, but these are the common choices of paths through the origin. And I think you're right. I think I would probably start with y equals x squared, because if you can, a goal that you're trying to kind of make happen when you have a limit like this is you would ideally prefer all of the powers in the numerator and the denominator to kind of be the same, which I think is what you're trying to get at with y equals x squared. If we pick y equals x squared, then we get the limit as xy. Sorry, I don't really want xy because I'm replacing the y's with x's. I'm just going to say the limit as x approaches 0 of 8x squared times x squared over x to the 4th plus 3x squared squared. And that totally ends up being the limit as x goes to 0 of 8x to the 4th over x to the 4th plus 3x to the 4th is for x to the fourth, which is the limit as x approaches 0 of 2, which is just 2. So great. Either the limit equals 2, or we're going to get a limit that's a different value. The limit's not going to exist. At this juncture, those are the only options, right? If one of the limits is 2, either all limits have to be 2, or you're going to get something that doesn't exist, which is way more likely. So let's pick a different path. Normally, I would pick the path y equals 0 or x equals 0, but I'm going to do something different. I'm going to pick y equals x and see what happens. So we pick y equals x, we get the limit as x goes to 0. I'm going to simplify it right away. 8 times x squared times x is 8x cubed, and x to the fourth plus 3x squared. Okay. So what am I getting if I plug in 0 here? Unhappiness, 0 over 0. So let's do some simplifying. What can I factor out from the denominator? Totally. I'm left with an x squared plus 3. And from the numerator, I can cancel an x squared with an x squared. I'm left with an 8x on top. So now I have the limit as x goes to 0 of 8x over x squared plus 3. And now I can totally plug in 0 and get 0 divided by not 0, which is totally fine. 0 divided by not 0 is 0. So look, 2 different paths gave me 2 different limit results, which means the overall limit does not exist. I do want to point out that it's almost, I don't want to say always, but very, very frequently, it is the right choice to pick one of these 2 paths because they're easy. If you pick y equal to 0, you're going to have the limit as x goes to 0 of 8 times x squared times 0 over x to the fourth plus 0. And before I take the limit, I'm going to simplify this. If I simplify that, what do I get on top? Way on the bottom. What's 0 divided by not 0? Always. What's the limit as x approaches 0 of a constant? Whatever that constant is. This is what almost always happens when you let one of them be 0. Is you almost always just end up making the whole thing equal to 0 in the first place, and then the limit of that ends up being 0. Not 100% of the time, but almost 100% of the time. This is what happens. Yeah. No, I'm just trying to point out that this is often a good choice. To me, this feels like a bit less work than this. But this one, combined with either this work or this work, is sufficient to show that this limit doesn't exist. Because we have one path being 2 and one path giving us 0.
So you choose to go through the y with x well.
Then we don't have to do this. I'm doing too much work here.
Oh,
I'm just showing you that if you wanted to do this, it's usually very easy to get the limit being 0 along one path.
you'd
And
be done with just showing that limit.
right. So you could do this one and either this one or this one, but you don't need to do both of these. I'm just doing too much work.
So let's say you were to do like trying to think.
It's okay.
I wrote it down.
Let me go to Jesus real quick. Wait by that.
I was just gonna ask, those are just 3 different ways that work, right?
These are 3 different paths that we are able to find the limit along those paths.
Okay.
And then I'll just mention, right? But either this and this show me the limit doesn't exist because one is 2 and one is 0. Or this and this show me the limit doesn't exist because one of them is 2 and one of them is 0. But if you did this one first and this one second, you wouldn't be done. Because you'd be like, oh, well, the limit so far is 0, but maybe there's another path where it's not. So if you keep getting the same result, you have to do it you could do it an infinite number of times and still end up finding, or not. You could do it like a million times, and on the million and first time, actually find a different value. So what I really want to stress is it's not enough to just keep getting the same value over and over and over again. If you think the limit actually exists, there's other work we're going to have to do.
If you were to plug in y for x, would you still get that number?
You would, yes. So whether we do y equal to x or x equal to y, we would get 0. So, right, if we did, let me just, if we plugged in instead x equal to y, we get the limit as y goes to 0. Now we're substituting in y for x, so we get, really it's just the same expression, right? It's 8y squared times y, which is 8y cubed over y to the 4th plus 3y squared. It's really the same exact expression, just with different variables, right? That's the same as that.
Okay.
Yeah.
So when I was doing it, because like I accidentally printed it doing that, I just could not get 0. I still got like my variable y inside.
Okay, so from here, what did I do here to simplify?
I was factored out y squared.
Right, so if I factor out y squared from, actually, you can do it from the top and the bottom. I've got y squared times 8y over y squared times y squared plus 3. And those cancel. And then I can plug in 0 for y now. If I plug in 0 for y, what do I get on top? Right? I get 0 divided by, importantly, not 0, which is equal to 0.
And then did you say that for if you do the y equals x or the x equals y, you only have to do that one, and you don't have to like pair it with another to prove it?
So we always have to do at least 2 paths,
Oh, okay.
right? We have to do 2 paths that give us different limit results.
Okay. So what were you?
So what I was saying is you could either have done this path and this path, because those give us different limit results. This one gives us 0, this one gives us 2. Or we could have instead done this path and this path, because this path still gives us 2 and this path gives us 0. But what would not have been enough work would have been if we had started with this path y equals 0, and then we did this path y equals x. Because both of those paths tell me the limit is equal to 0. Well, so far there's agreement. So as far as I know, the limit might exist and be 0. So I need to do more work. And the work I'm going to do is pick another path. I would say if you're using this path method, you should at least try 4 paths before you decide you think the limit might exist. And even then, it probably doesn't. Probably isn't even too strong there. It's a pretty good chance. There's usually a good chance your limit doesn't exist. Let's look at some more examples. And let me make sure, let's see. 3, okay. I want to leave enough time to talk about partial derivatives. Let's look at this example. An example that does not go through the origin. The limit as xy approaches 1, -1 of x plus y over the product xy plus 1. All right, so here it's a 0 over 0 type stuff. So we need to pick some paths. Well, I should say, I'm always approaching a limit with the thought that it probably doesn't exist in this class, right? Not like in 17A, but in 17C, most of these multivariable limits, I'm always coming at it with like, you probably don't exist. I'm going to start using paths to try and show you don't exist. And then maybe you'll prove me wrong and actually exist. But usually we're always starting with like, I really think this limit doesn't exist. So let's pick some paths that go through this point. 1, -1. What's a line or a question? Excellent, Joyce. Y equals -x. There is a good path. It goes to that point. So the limit as I'm going to replace y with -x. So I'm going to get x approaching +1 of x plus -x over x times -x plus 1. Okay, so let's see here. That's going to be the limit as x approaches 1 of x plus negative x is 0 over negative x squared plus 1. What do I do now? So if I plug in the 1, what am I going to get? 0 over 0, which is what I'm trying not to get. So I actually don't want to plug in 1 yet. I want to do more simplifying. How does this expression, 0 divided by negative x squared plus 1, how does that expression simplify? Say that one more time. I actually can do less work. Sorry, I'm just letting the people on Zoom know they can ask questions. Is the denominator 0? It's not. Right? I know we might think it is, because like when you're saying like x is 1 and then you get negative 1 plus 1. But remember, x is not actually 1. It's just close to 1, which means your denominator isn't actually 0. It's just close to 0. So x could be something like 1.001. What if x was equal to 1.001? Well, then 0 divided by negative 1.001 squared plus 1, what would that equal? I mean, the denominator is something. I mean, it's really, okay, it's negative 1.002001 plus 1. That's going to be 0 divided by negative 0.002001. Okay, what's 0 divided by negative 0.002001? 0, right? That's the whole point. I don't actually care. We never should have really done this. I don't really care what the denominator is, except that I do care that the denominator is not 0. And so then 0 divided by it gets to be 0 before we take the limit. And then the limit of 0 is 0. That's the whole deal. But we're not done, right? Because we've only done one. One path is never enough paths. So we need to pick another path.
So because there was a 0 in the numerator, it would have been 0 regardless.
Right. Once you get 0 in the numerator, as long as the denominator isn't also exactly 0, right? Not plugging in the limit, just saying like, is the denominator 0? No, it's not, right? It's not just 0. We're good to go. 0 over any non-zero thing is 0. Excellent path. What's another path that goes through that point? We just use that one. There's some really easy straight lines that go through that point. Like that one. What's that line? Right. There's a perfectly good path. So if you have especially if you have a point, you have a point that is not the origin, it usually makes sense to pick paths that are straight lines first. So usually a horizontal line, a vertical line, always easy. And then you can also y equals negative x is a great choice here. So if we pick y equal to negative 1, let's see what happens. We get the limit as, well, since y is negative 1, we only have to worry about x approaching 1. And then we have x minus 1 over negative x plus 1. I'm going to rewrite that to make an observation. Limit as x approaches 1 of x minus 1 over 1 minus x. What's x minus 1 divided by 1 minus x? Well, you might say, well, James, it's a variable, so it's going to change. I would say yes, but what's 6 minus 2 over 2 minus 4? So, oh my God, James. That's not the question I meant to ask. What's 6 minus 2 over 2 minus 6? What's 83 minus 17 over 17 minus 83? Okay, see what I'm talking about? If you subtract things in the opposite order and divide them by each other, you're always going to get -1 because this is just the negative of that. This is just the negative of that. This is just the negative of that, or vice versa. This is just the negative of that. This, or you could also do the algebra and actually factor out a -1 from either the top or the bottom. That would also be perfectly fine. You could say this is equal to the limit as x approaches 1 of x minus 1 over -1 times -1 plus x. And x minus 1 is the same as -1 plus x. So that's equal to the limit as x approaches 1 of 1 over -1, which is the limit as x approaches 1 of -1. And the limit of a constant is just the constant. And oh, look, different values. Our limit doesn't exist. Another good path to choose for this one would have been the path x equal to +1. That's another excellent choice of a path. Right. Let's look at another one. This next one's going to be exciting. You found these ones boring so far? Prepare to be thrilled. Not really. I mean, you might be interested. Thrilled is a stretch. Limit as xy approaches 0, 0 of 2x squared y over 3x squared plus 4y squared. And once again, it's definitely 0 over 0 type. No big deal, right? I mean, most of the limits you're going to see are going to be 0 over 0 types. So let's look at some paths. I'm going to pick y equals 0 as a path. Make the limit as x approaches 0 of, if y is 0, I'm going to get 0 on top. And if y is 0, I'm going to get 3x squared on the bottom. 0 divided by any non-zero number is 0. So I get the limit as x goes to 0 of 0, which is 0. Okay, great. So now I need another path that gives me not 0. So let's try y equal to x. So the limit as x approaches 0 of 2x squared times x over 3x squared plus 4x squared. Okay, that's going to be the limit as x goes to 0 of 2x cubed over 7x squared. You can cancel an x squared. You get the limit as x goes to 0 of 2x over 7, which ends up being 0. Okay, another path. Try y equals x squared. Limit x goes to 0. 2x squared times x squared. The bottom of 3x squared plus 4 times x squared squared. Seems good so far. Limit as x goes to 0 of 2x to the 4th over 3x squared plus 4x to the 4th. And here's where you should do the thing where you factor out the biggest power back to the denominator, right? If these powers don't match, do some factoring. So I'm going to write this as the limit as x goes to 0 of 2x to the 4th over x squared times 3 plus 4x squared. Cancel an x squared here and an x squared there. I'm left with the limit as x goes to 0 of 2x squared over 3 plus 4x squared. But that's going to be 0 over 3, which is 0. I'm getting a lot of zeros. This limit might be 0. And so if you, I know I said you should do at least 4. I know this one's not. I know this one is going to be 0. So like, if we kept trying more paths, we would keep getting 0. And that's because the limit here actually is equal to 0. So the question now is, how do you show a limit is equal to 0? Or whatever it happens to be equal to? Well, it can be challenging. Normally in this class, there's kind of one typical way people show them to 0. So here's what we want. This is my function, f of x, y. I would say it's 2x squared y over 3x squared plus 4y squared. And here's what we want to say. If this limit actually is equal to 0, here's what should be true. It should be true that f of x, y should be close to 0 as x, y approaches the point 0, 0. So another way to say that is for something, so if you want f of x, y to be close to 0, what you're really saying is the distance to 0 should be small. If you want something, if you want a function to be close to a particular number, the way we kind of express that mathematically is by saying the distance to that number should be small, as small as you want. So I want to talk about the distance from f of x, y to 0. Okay, let me ask you a different question. What's the distance from 0 to 7? What's the distance from -7 to 0? Also 7. Right, so the point is that whether the difference between them is something that you might find negatively or positively, we still express distance as a positive value. Right? Distance is always positive, it's never negative. So the distance between two things is expressed as the absolute value of the difference. That's what we want. And what we want to show, we want to show that this distance can be as small as possible. Okay, well, let's actually write in the function that we're dealing with, right? So we want to show that this distance, and the function was 2x squared y over 3x squared plus 4y squared. Minus 0, I didn't write that. Okay. So let me point something out. This is equal to this. The reason I can pull all of this out, let me ask you, can 2x squared divided by 3x squared plus 4y squared ever be negative? No, everything is to an even power. It could be 0 over 0, but we're not worrying about that. We're only asking, do we really need the absolute values? And the answer is no, because the insides are never negative, is what I should really say. So great, we can drop the absolute values that one. But the y could be negative. And you can totally approach 0, 0 from a under, right, where y is negative. So we need to leave the y inside the absolute value for now. Now we're going to make an observation. I'm going to start with this. 2x squared, definitely less than or equal to 3x squared. True? We can graph it, right? Here's like 2x squared. Here's 3x squared. 3x squared is definitely always bigger than or equal to 2x squared. For sure, 100% all the time. Even if x is negative. All right, well, if 2x squared is less than or equal to 3x squared, then it's definitely less than or equal to 3x squared plus another non-negative thing. All right, if I'm adding on a positive number to the side that's already bigger, it's going to get even bigger. And now for the fun part. Okay, I'm going to divide both sides by something. If I were to divide both sides by a negative, I'd have to worry about changing the direction of the inequality. Fortunately, I'm not. I'm dividing by both sides by something that I know is positive. Well, look at that. 2x squared divided by 3x squared plus 4y squared is less than or equal to 1. It's true. For sure. Absolutely. You can graph it. Can we graph it? Let's find out. I feel like there's something screwy going on with this graphing program, but I think we can maybe we'll find out. Come on, what's going on? Oh, there we go. So I think I need to use f of x, y, I think I found last time. But if we graph this thing, let's take a look. 2x squared. Ooh, that's fun. Divided, oops, not divided by there. Divided by 3x squared, that's boring, plus 4y squared. Let's see, definitely, if you move it around a little bit, yeah, those values are definitely less than 1 for sure, and positive, right? All those output values are certainly above the xy plane and well below 2/3 actually, is what they're well below, but definitely below 1. So cool. Definitely less than 1, and importantly, bigger than or equal to 0. For sure, it's bigger than or equal to 0. Right? It can never be negative. Okay, great. So be prepared for the squeeze theorem here. This thing right here, 2x squared over 3x squared plus 4y squared. I'm just going to take that. I'm going to take that, which I already know is between 0 and 1, and multiply everything by the absolute value of y. And 0 times anything, still 0. Great. So now we're going to take the limit of each of these parts. What's the limit as x, y approaches 0, 0 of 0? Everybody. Thank you. Yes, everybody now.
0.
Thank you. Right, the limit of a constant, just the constant. That's going to be less than or equal to the limit of this part. And that's going to be less than or equal to the limit as x, y approaches 0, 0 of this part. But what's the limit as x, y goes to 0, 0 of the absolute value of y? Well, where's y going to? It's going to go to 0, which means this limit has to be 0. Oh, look, the thing we're trying to find the limit of is bigger than or equal to 0 and less than or equal to 0. It's got to be 0. It's getting squeezed to 0. That's what's happening. I'm not going to go there. So, right, our limit is above the plane 0 and below this other thing that's getting smooshed down to a point 0 at the origin. Yeah, this is often how we show limits exist in this class, by finding some sort of squeeze theorem or sandwich theorem way of showing it. And it often involves recognizing that a bunch of stuff is positive and less than or equal to 1, and then multiplying it by whatever's left over, and then using the squeeze theorem. We'll do something like that. What time is it? 2:35. We'll come back to that. We'll do another question.
Before you divided the 3x squared.
Mm-hmm.
That is 3x squared less, or I mean 2x squared less than 3x squared.
So to show, to get what I wanted, really, I wanted to get this less than or equal to 1.
But did you like already know that?
I did kind of already know it. Yeah, that's totally a very relevant point. I knew where I was going with this, for sure. I know there's a problem. I think there's a problem in the textbook that looks something more like, I forget what exactly it was. It was something like 3x squared over 3x squared plus y squared. And then there's also a y there, something more like that. The thing we have to be able to kind of get used to seeing, and again, I don't really know how much your professor is really going to need you to be able to do this, is to recognize this is a fraction. And in that fraction, is the denominator always bigger than the numerator? Yeah, it is. Because the denominator is the numerator plus something that is always bigger than or equal to 0. And if the denominator is always larger than the numerator, the fraction is always less than or equal to 1. So that's what I was really using here. I was saying, well, look, I know that 2x squared is always going to be less than or equal to 3x squared plus 4y squared, which means this fraction is always going to be less than or equal to 1. And I was trying to kind of show it in a, what I hoped was a thoughtful way, where I started with this, and then I added 4y squared to the right side. And then I divided both sides by that. That was the thought process there. So yeah, I will admit, it's not always super obvious, like what exactly we need to get to. But if you are of the opinion that a limit might exist, this is the kind of thing you want to try and look for. Try and kind of pull out the things that are all to even powers, because that's usually the kind of examples that they're going to make work this way, and try to say something about what that fraction value has to be between. It's not a perfect process, but it does usually. And we'll see that one. We had another example. I think it's worth our time to, because we only meet Tuesdays, Thursdays. We should definitely spend some time talking about partial derivatives. And yeah, there's definitely a favorite example I have. And I want to make a blanket statement starting off here, is that partial derivatives should be easy. Meaning, if you know how to do it, it's easy. Whenever you're doing a partial derivative with respect to, you do need to talk about what variables. So we're taking the partial derivative of a function with respect to x, we are pretending like y is a constant. So if you really like, in fact, let me just do a couple of examples that are easy, and then we will move on to actually what I want to do. So let's say our function was this. This pen is trash. Let's say our function was x to the 5th plus 2x cubed y to the 4th minus 6y to the 7th plus 9. And I'm going to find the partial derivatives here. The first partial derivative. You can either write it, so I'm going to find the partial with respect to x. You can either write it as f sub x is one notation, or you can write it as del f del x. It's not a d, it's a little bit curlier d, which is called a del. Not the same. So what's the derivative of x to the 5th? What's the derivative of 2x cubed? what's the root of 2x cubed times a constant? 6x squared times that constant. So as far as x is concerned, right, when you say del f del x, you're asking, how is the function changing as x is changing, or as you're moving back and forth in the x direction, not moving in the y direction at all? Y is staying constant. And I'll remind you, if your function was 2x cubed times 3 to the 4th power, what would the derivative of that be? It'd be 6x squared times 3 to the 4th. Because that 3 to the 4th is just a constant multiple. And when you have a constant multiple of a function, you're differentiating, I just like to say the constant multiple hangs out. Right? It doesn't become 0 because it's not on its own, it's multiplied by x. Or you could actually do the simplification here, right? This is really 3 to the 4th is 81 times 2 is 162, x to the 3rd. And then the derivative would be 3 times 162, times x squared, which is exactly what this is. 3 to the 4th times 6 is 486. So the whole point there, though, is that if you have a multiple of a function that's acting like a constant, it hangs around like a constant. We just get 6x squared times y to the 4th. All right, here's a different question. What's the derivative of 6y to the 7th? Equals 0, because it's acting like a constant. It's like 6 times 3 to the 7th. And the derivative of 6 times 3 to the 7th with respect to x, well, there's no x's, so the derivative is 0. So there's my partial derivative with respect to x. It's 5x to the 4th plus 6x squared y to the 4th. And the thing to really take to heart is that when you're differentiating with respect to x, you treat y like a constant. And then the other way for the other partial. I'm trying to find del f del y, or fy. Derivative of x to the 5th, 0. Derivative of 2x cubed times y to the 4th is 2x cubed times the derivative of y to the 4th, which is 4y cubed. The derivative of 6y to the 7th is 42y to the 6th. Plus 0. And then we could simplify that as 8x cubed y cubed minus 42y to the 6th. So when I say it's easy, what I mean is it's easy if you remember that you treat the other variable like a constant, because then it's just your usual derivative rules from 17a. Power rule, quotient rule, product rule, chain rule, et cetera, et cetera, et cetera. All right, so now I want to back up a little bit because there is some very important geometric kind of stuff we need to be aware of. And I'm going to cheat a little. Yeah, these are good pictures. Grant makes some good pictures. I'm not ashamed of using someone else's work. So, talking about partial derivatives. You can find all this stuff on Grant's 17A website. I think it's worth everyone looking at. And I would draw it myself, but I know that my picture is never going to look as beautiful. So that's all right. So here's the function. F of xy is 9 minus x squared minus y squared. And if you graph it, right, we could find the traces. The traces in the 3 different systems would be, back this up for a second here. Right, in the xy plane, where z is equal to 0, we would get 9 minus x squared minus y squared equal to 0, which gives us x squared plus y squared equal to 9. We get that circle right there. That's our trace in the xy plane. In the yz plane, where x is equal to 0, we get 9 minus 0 squared minus y squared equal to z. So z is equal to 9 minus y squared. we get this downward opening parabola with intercepts at 3 and -3 and a z-intercept at 9. And the same thing in the xz plane. We get, well, we have y equal to 0, and we have 9 minus x squared minus 0 squared equals z, which becomes z equal to 9 minus x squared, which is just, now we haven't actually drawn it, which is totally fine, but it would be that downward opening parabola right there in the xc plane. So there are your 3 traces. And now what I want to say is, let's imagine we're at the point 1, 2, 4, which is right here. You've gone 1 in the x direction, 2 in the y direction, and 4 in the z direction. Like that. It's kind of fun. If you face yourself, oh, yes, let's make sure you can all see that. There, sorry. So if we face towards the positive x-axis, which means we are facing, if I'm standing at that point there, I'm facing that way. If I travel in this direction, am I going up the hill or am I going down the hill? I'm starting there and I'm moving that way. What is it? Up or down? I'm going down. Right, so I'm moving out away from that point right there. I'm coming down this way out towards you. Sorry, I should be making it clear so everyone can see this, right? If I'm here, I'm moving. If I'm moving in the positive x direction, that is the towards you direction from this page, and I'm moving down that way. Okay. I should also mention, I'm traveling that way. I'm traveling along the trace of y equal to 2. Right, so I'm holding y constant. Right, if I'm traveling on this section here, the y value isn't changing. I'm just moving forwards. I'm not moving left or right. So I have a constant y value. So what's my derivative going to be? Well, if I take the derivative with respect to x of 9 minus x squared minus y squared, that's not hard. It's 0 minus 2x minus 0. So my derivative is negative 2x. And if I evaluate it at the point I'm starting at, it's going to tell me the slope in that direction. So if I plug in x equal to 1 and y equal to 2, well, there's nowhere to plug in y. If I plug in x equal to 1, I get negative 2. So my derivative in that direction is negative 2, meaning if I start at that point and travel forwards, I'm going to be going down in the slope of negative 2. I'm going to be going 1 forward and 2 down. On the other hand, if we move in the positive y direction, which is which way? Up, down, left, right, forward, backwards. There's x, there's y, there's z. Which way? Point. Point in the direction that is the positive y direction. That way. Right? Whoops. Sorry, I keep wanting to like, right? If that's y, if that's the positive y direction is to the right. So typically when we're talking about the XYZ coordinate system, the positive x direction is out of the page towards you. The positive y direction is to the right, and the positive z direction is up. This is what's called the right-hand rule. You point your fingers in the positive x direction and you curl them towards the positive y direction, your thumb should point in the positive z direction. It's more important for physics and torque kind of stuff, but it is something that's also true when you're setting up your XYZ coordinate system, is it should obey the right-hand rule. So if I move in the positive y direction, I'm going to be moving along the trace where x is equal to 1. I'm going to try and make happen here. It's always a challenge. Almost got there, and then blew it at the end. Sorry, it should look more like that. So we're moving along this trace to the right. So again, we're moving down the hill. Now, when we move down the hill to the right in the positive y direction, we're actually moving at a steeper slope. And if we find the partial derivative there, well, the partial derivative is still going to be kind of the same, right? The derivative of 9 minus x squared minus y squared with respect to y is going to be negative 2y. But when we plug in the point 1 comma 2, we get a value of negative 4, meaning the slope going that way is over 1 down 2. The slope going that way is much steeper. It's over 1 down 4. And hopefully some of you have at some point gotten out in the hills somewhere, done some hiking. It's fun. It's a good time. But you've probably noticed if you've ever hiked up or down a mountain or a hill or some sort of slope surface, different directions have different steepness. And usually you're traveling up the least steep path, right? You're going like around some switchbacks or whatever. But sometimes you may be like, I want to go fast. Instead of going up the switchback, you make a sharp turn, you go up like that, right? That's the difference here. The direction of travel dictates your steepness. Or really, honestly, it's more that the steepness dictates your direction of travel. Different directions have different slopes. All right. We can also take other derivatives. But I really want to emphasize here, these partial derivatives do have physical meaning, right? There, you're talking about the slope of this surface in a particular direction. The most common directions being the towards you direction and the to the right direction. And those are the most common directions because those are the partial derivatives with respect to x and with respect to y. That doesn't mean they are the only directions we ever consider. They're just the easiest ones to think about at first. All right, let's talk about other derivatives we can find that coincide with this. I mean, I should. So we can also find second partial derivatives, which for this function are not super exciting, right? If f of x, y is 9, sorry, brain. Right, fx, which is del x is negative 2x. And the second partial, which you can either write as fxx or del squared f del x squared, which is really just the partial derivative of the partial derivative of f. What's it going to be? What's the derivative of the derivative here? It's kind of boring. Yeah, it's negative 2. What that does tell us is about the concavity. Right? The second derivative tells us if a function is concave up or concave down. So what this is telling us is that in the x direction, it's concave down. And similarly, fyy, which is del squared f del y squared, which is del y of del f del y, that's also negative 2, which tells us it's also concave down in the y direction. Now, there's also the mixed partial derivatives. So this is something worth being aware of. Hopefully your teacher only uses one type of notation, but he might use both. Del squared f del y del x says we're first going to take the derivative with respect to x and then with respect to y. We read this derivative notation from right to left. It is the derivative with respect to y of the derivative with respect to x, which is going to be the derivative with respect to y of negative 2x, which is what? Kind of the most boring answer you can get. 0, right? There are no y's there. the derivative with respect to y of something that doesn't have any y's in it has to be 0, because as far as y is concerned, all of that's a constant. And this, and yeah, and the same thing the other way. If you did del squared f del x del y, which is del x of del f del y, which is del x of negative 2y, it's also going to be 0. Couple things to be aware of. This is where the notation is annoying. In the other notation, this is written as fxy. So when you use this notation, you do read from left to right. This notation here says take the derivative with respect to x first, and then the derivative of that with respect to y. That's also what this notation says. This says do x first, then do y second. Just be careful, they are in the opposite order of each other. And then this one would also be fyx. Any function you encounter in this class should have the mixed partials in either order ending up being the same value. So it is not always true, but it is generally true that fxy is equal to fyx. There are counterexamples to this. They are complicated. They're very contrived, is what I'll say. You have to work hard to make up a function that doesn't satisfy this statement. It's a complicated piecewise function. It's kind of the easiest example of a function where this is not true. So if you're looking at a function that's like just like regular x and y's, there isn't anything kind of out there about it, you can be very sure that you're going to have something where the mixed partials are the same. All right, so let's look at some other examples. Yeah. Oh, that's a good point. I should say that. I know I already kind of said this, but I want to make it really, really obvious. This is actually, I'm glad I'm looking at this thing. Grant system things. So f of x equals sine of x plus 3. What's the derivative? It's not meant to be a complicated question. The derivative is, I heard someone whisper it, cosine x plus 0. On the other hand, if your function is 3 times sine of x, what's the derivative?
3 cosine of x.
Thank you. The point I want to really drive home is that when you have a constant by itself, its derivative is 0. But when the constant is multiplied by a function, it hangs out. It sticks around. That's what I was trying. That's well, that goes back to the example we said before. Oh, where'd you go? Right. That's why in this example over here, when I take the derivative of this with respect to x, that y to the 4th constant is hanging out because it's a constant multiple of a function. Let's look at a couple more examples because yeah, we've got 1 minute. Let's maybe not look at more examples and just I should stop. I could say more. What I will say is definitely fill out the attendance form. But what I also really want to say is you can totally look at this handout on Grant's website. I think it's worthwhile. It's got some more examples of partial derivatives. But really the thing to remember is we differentiate with respect to x, treat y like a constant. We differentiate with respect to y, treat x like a constant. And if it really helps, like for example, if you have to differentiate something like, I don't know, f of xy equal to e to the x cubed plus sine of y, and you're doing fy, I might, if I was really like, how do I do fy? I might rewrite this as, I'm going to pretend that x equals 2 for a second, and rewrite my function as f of 2 comma y is e to the 8 plus sine of y. And then say, okay, well, I know what the derivative of that is. The derivative of some stuff, sorry, the derivative of e to some stuff is e to the stuff times the derivative of the stuff. What's the derivative of 8 plus sine y? 0 plus cosine y. But then really that 8 isn't 8. That 8 is really x cubed. So my derivative is actually e to the x cubed plus sine of y times 0 plus cosine of y. So sometimes you don't have to do this, but if you're not sure what's supposed to happen, sometimes replacing the variable that you are not differentiating with respect to with a constant can help you see what's supposed to happen.